Hi, Tov. Today we're going to be looking at the Ester chemistry that you need to learn. So there isn't any mechanisms in this. There's quite a lot of rote learning, really. So you just need to memorise quite a lot of this stuff. It's not too complicated, really, but it's a bit bulky. So the first thing we're going to look at is how we synthesise. So how do we synthesize esters? So firstly, just the general structure of an ester. So all esters, you should know this, but they all take the form. This, I've done this as R and R prime. They can be the same, they can be different from each other. Now, we can sort of divide this molecule up into two halves. If we break it down, the ester link, or the ester bond, we've got the alcoholic section and the carboxylic acid section. You don't have to form them by from a carboxylic acid and an alcohol, but that's a very common way of doing it. So we're going to take the carboxylic acid and we can take the alcohol, and those two will react with each other to form the ester. Now, if you just put them together, that reaction is mind-numbingly slow. So instead, we need to add a catalyst, and it's in a equilibrium reaction. So if I'll draw an actual molecule this time. So we'll take methyl ethanoate. So this is methyl ethanoate. And that is in equilibrium with the acid and the alcohol. So we've got ethanoic acid and methanol. So in terms of synthesizing the ester, we'd be going the backwards reaction in this one. Now, we don't have to draw the mechanism of that output for these. Sorry, you do it at university level rather than A level. But we do need to be able to sort of name the reactions. So going this direction, other way around, going left to right, you are breaking that ester bond. So you are cleaving it along this line here. So, and you do that using water generally. It's the water that actually causes that to break. So we call that hydrolysis. Now, hydro is in water, lysis is like the Greek word for to break something. So we saw in the radical chemistry, you saw homolytic fission, so breaking the bond in like the chlorine or the bromine molecule using UV light. And you saw homolytic, and it's the same sort of root as lysis. Now going the other way, so combining these two together to form the bond, actually form the ester bond, that's called a condensation reaction. And it's called condensation because we're going to be removing water. So this net removes the water molecule when we go from here to here. So you could almost have plus water on this side. Now for the condensation, reaction, so the actual forming the ester, the conditions is that you need an acid catalyst. So if you put those two together, I don't know how long, but probably weeks to even reach equilibrium. If you add an acid catalyst, that will occur faster. It's still going to take many hours. It's definitely not a fast reaction. It's that acid catalyst. So something like HCl or H2SO4 or H3PO4. Just normally pick one of those two at the front. Either of those. So if you've got a strong acid catalyst, don't choose. You're not going to use a weak acid catalyst like ethanoic acid is a weak acid. You need a strong acid. Now, the product that's formed, you're not going to form a nice pure product. So you're going to end up with a horrible equilibrium mixture of all of these, and so you're going to need to go and purify that. And so the best way you're going to be able to purify that, so it's a bit tricky. So I think the one you expected to know for your A level is that you're going to use, the simplest thing is always just distillation. So you could purify this by distillation. I think in reality, certainly in a lab setting, you'd use something called solvent extraction. So I think the guys that came on the trip to Oxford right at the start of the year, you do a solvent extraction. So you use that secretary funnel, the big bulbous thing with a tap at the bottom that you shake, and then it forms 2 layers. And because this would be quite soluble in the alcohol in the organic layer, so this would dissolve quite well in an organic solvent, sort of oily solvents, whereas these are much more soluble in water, and water and oil are immiscible. They form 2 separate layers. So you take this reaction mixture, let's say it was done in water, you'd add a load of an oily solvent, so an organic solvent is more the language we use in chemistry. So, for example, dichloromethane or diethyl ether. Give it all a good mix up, a good shake, and then those 2 layers separate from each other. So you'll have the oil on the top and water on the bottom, and these will end up in the water layer at the bottom, and our actual desired product will be in the organic layer at the top. And so you just discard the water, and you'll purify. It won't be completely pure because some of this will dissolve in the oil layer, and some of this will dissolve in the water layer, but you will be able to separate it reasonably effectively like that. A distillation probably could give you a much purer product. The only consideration is you've got to think about how thermally stable some of these things are. So sometimes molecules can decompose before they boil. I don't know if that applies to these. It's probably perfectly reasonable to distill all of these over at different points, but that's something to bear in mind. And it's quite energy intensive. It takes a lot longer than doing a solvent extraction. Now, some of the uses of the esters that you form. So they're sometimes used as flavourings. So some of these very short chain esters, they're very chemically smell to them. You wouldn't want to use them as a flavouring. But once you get up to sort of the 4 and 5 number of carbons on either end, a lot of them have got really quite very, very pleasant fruity smells. So sort of peaches and some of them are banana and apple and orange. Some of them are really, really nice. Ones that are mint. And you can actually look it up if you look up like a table of different smells of esters. I remember seeing quite a good table where it had the number of carbons on the left hand side and the right hand side in a big grid, and all the different smells associated with them. So they're used sometimes as flavourings, and I'm trying to think of a word for odorants maybe. So used for their flavour and their nice smells. So the classic example that chemistry teachers like to use is that of pear drops, and that pear drops have esters in them. Normally I think it's just an excuse to bring sweets into the class. The other one that you expect to know about is plasticizers. So you've got in a plastic, you've got the polymer chains, and they tend to be generally very long, very straight polymer chains, and there's quite strong van der Waals forces between each of those chains, and that can make them quite brittle and inflexible. Now, a plasticizer is a molecule you mix in that gets in between those chains, just spaces them out a bit, and that reduces the strength of the intermolecular forces between the chains, which makes it more flexible. So you're trading strength and rigidity for flexibility, and so the addition of those plasticizers just allow you to tailor the properties of that plastic a little bit more. And esters are a molecule that you can use for that. I've never really run into doing that myself, but it's on the A-level specification. You're expected to know. So plasticizers, esters are used as can be used as plasticizers, and they make the plastic more flexible. Now, you haven't done necessarily all of your equilibrium chemistry yet, but an interesting thing to think about is how we can, certainly when we're going from right to left, so doing the condensation reaction, which does produce a 1 molecule of water, so if I add that to our equilibrium, and you're trying to drive this to the left, things you can actually do to help drive that reaction to move further to the left. So you can do things like playing around with the temperature. I don't know which way is actually favoured in terms of temperature. Don't know if it's endo or exothermic. There's probably not much of a difference, but there is something you can really do that it won't come in your A level, but I think it really strongly links to your equilibrium.